All right, they should be up now. Right, just take a second and then compare your answers to someone near you. The reason I'm asking you about these particular algorithms is because some of the ideas today, even though we're going to be talking about AlphaGo and Monte Carlo tree search, will be related to some of the things that helped make those advances possible. So just check, a good chance to refresh your understanding of how upper confidence bound algorithms work. And the one I thought might be somewhat controversial in particular is the third one, of whether or not if you have a reward model and it's known, whether there's still any benefit to using an upper confidence bound algorithm. All right, let's come back together. So looks like there was good agreement on the first couple. So the first one is true, which is you can think of upper confidence bounds as being a way to balance between our uncertainty over outcomes when we have limited amounts of data, and yet use that information to still try to acquire high reward. And these algorithms can be used both in bandits and Markov decision processes. The third one is a little bit tricky. Actually, either answer would be fine, depending on which setting you're looking at. So does somebody want to argue why, if the reward model is known, there is no benefit to using upper confidence bound algorithms? So in some settings, there would not be. Someone tell me a setting where if you knew the reward model, you should not use an upper confidence bound algorithm. Something that we saw over the last couple of weeks that was different than the reinforcement learning framework.
The multi-arm bandits.
That's right, yeah. So in the multi-arm bandit case where there's like no state, there's no dynamics, the decisions that you make don't influence the next state at all, then exactly what said, if you knew what the reward model is, you'd know how to act. Like if I knew whether a customer liked ad A or ad B better, I would just show them ad A. So in a multi-arm bandit setting, so in a map setting, this is true. In general, it's not true. In RL setting, generally false. Somebody want to tell me why in general it's false? Even if you know the reward model in reinforcement learning, you might still want to use an upper confidence bound based algorithm.
Because what we want to know is the value function rather than just the immediate reward?
That's right. So assuming that you don't know what you said, which is assuming you don't know the dynamics model, so you don't know how to compute what your optimal value function is, it's still often helpful to use upper confidence bounds. And in fact, in many cases, you might know the reward function for when you reach a state, like you know when a customer clicks on something that's good, but the hard thing is maybe to drive them into states where they are going to click on something or they are going to make a purchase. So in RL, this is generally false, and we'll see some other examples today where it's helpful to use an upper confidence bound algorithm, even though we know quite a lot about the world. So what we're going to be talking about today is Monte Carlo tree search and AlphaGo. And before we get into that, I'll just remind us a little bit about where we are in the course. So we have just a few more weeks left. You should have all gotten feedback on your projects. I encourage you to come talk to me or anybody else about any questions you have. I have 2 office hours this week because I was traveling late last week for a conference. So you're welcome to come to my office hours today, which are right after this class, or on Thursday. And there's also a lot of other office hours. In addition to that, a week from this Wednesday, we're going to have a quiz. The quiz will send more details out about on Ed, but the main idea is that it's going to be multiple choice. It is designed to be easier than the midterm, but we'll give you the full amount of time. People generally take the full amount of time just to check their answers, and it'll cover the entire course. So everything up through, the day before. Somebody had any logistics questions before we get going? All right, so we're going to talk about Monte Carlo tree search and AlphaZero. So as many of you may know, there was this amazing series of results from DeepMind in kind of like the 2016 to 2019 time period around showing how you could use reinforcement learning and AI to conquer the board game Go. And this happened about a decade earlier than people expected. And this was really considered one of the huge achievements in AI. So people really thought it was going to take a lot longer to do this. Chess had already been mastered, checkers longer before that. But there was a lot of different innovations that came out of a long history of work that DeepMind used to make this possible. And I also think that it incorporates a lot of interesting different ideas that one might think could be helpful to try to solve other problems. The other thing that I think is interesting about this is it's quite a different form of reinforcement learning than we've seen before. It's really reinforcement learning for computation, and we'll see a lot more about that. Okay. So what we're going to start with is thinking about simulation-based search. And simulation-based search is going to sound quite familiar because we've been seeing ideas around this with Monte Carlo search, Monte Carlo methods. But then we're going to think about combining these with using different parts of the sort of stochastic decision-making process. All right. So in particular, one of the major ideas that we're going to be looking at today is the idea that we're going to be mostly focusing on how to figure out what we should do in the current state only. So in general, in class, whenever we've been computing a policy or a value function, we've been computing it for the entire state space. So we might have a policy, and if anybody gave us a state, we could immediately tell you what action or action distribution we should use. Or we compute a Q function for the whole space. One of the key ideas today is to say, well, maybe, particularly if we've got an enormous space, that we don't really care about trying to compute an optimal policy for everything in the space. Maybe we just want to use our computation to really focus on a good decision for right now, or for whatever state that you might end up in. And there are lots of reasons to think that that might be important, particularly in really large domains. So you could imagine, if you're the Fed and you're trying to make a sort of federal monetary policy, you probably don't care about doing this for all the scenarios which the US is not in. You really want to figure it out for the current scenario. In the case of the board game Go, as we'll see, there's just an enormous space of potential states you could end up in. And it may not be important to have a perfect way of acting in all of those. So one big idea here is that we're going to be mostly focusing on computation to figure out what's the right thing to do in the current space. So one thing you might do in this case, given all the ideas we've seen in class, is you might simulate. So imagine that someone gives you a policy, and what you want to do is try to do at least as good as that policy and maybe a little bit better. So one thing you could do is say, well, I'm in a current state, like a current real state, say ST, And what I'm going to do is I'm going to say, think about all the different actions I could take next, and then I'm going to roll out using my default policy from those states. So this is just like for k episodes from the current real state, I'm going to roll out in my brain what might happen. Now this means that I need some access to a dynamics model. So I can only do this if I have access to a model, and what I'm going to mean here by model is dynamics and reward model. So you might imagine that you actually know how the world works, or that you've learned some sort of model from the past. This could be estimated or true. And so then what we can do is we can just do sort of Monte Carlo evaluation. And what we're getting here is an estimate of the Q function that says if I start in this state and I take this action, and I roll out under my simulation policy, what is my expected return? So that just gives me an estimate of the Q function. We've seen this before with Monte Carlo methods. And then you could just pick whatever the real action is, like this is what you're going to take in the real world, with the maximum value. And what you can think of what this is doing, and I'm just going to augment this with pi to make that even more clear, is what I'm essentially computing is, from the current state, what is the Q value of my simulation policy? And so I could roll out under those policies, and then I'm going to do sort of one step of policy improvement, given that. And so if someone gave you a budget of computation, this would be one reasonable thing you could do with it. And then we're going to see a lot of things that you can do that are much better than this. But this is one thing you could do that would be viewed sort of as simulation-based search, which would allow you to do better than the current policy you have. All right. I think it's helpful to think about this in terms of sort of what the tree structure is. So the idea in this setting is that we start in some state, and we're going to roll out under, or we're going to take a certain action. So that's going to be our action A. Label it here. That's our action A. And we will, and then after that, we're going to get to another next state, S prime. And then from then onwards, we're going to follow our policy pi. So this here is policy of S prime. We're going to sample an action according to that. So at the root, for my current state, I'm going to consider all possible actions. But then after I take that action and transition to a next state, I'm just going to roll out by following my policy pi. Okay, and then I do that all the way out till I hit a terminal. So T here equals a terminal state. And so one thing you could do is just do the simulation and then average over the root nodes, but you also now have a whole bunch of data, so you could do other forms of reinforcement learning given that data.
Doesn't the pi need to be fairly optimal for this to give an accurate guess?
Good question. So it depends how we think of what this is computing. So if this is just computing Q pi of SA, it's just doing one step of policy evaluation. So this will work whether pi is a good policy or a bad policy. But exactly, I think to the point, if pi isn't very good, then you probably aren't going to get a very good, like you're just doing one step of policy improvement here. You're not necessarily going to get Q star, okay, unless pi is really close to optimal. Okay, so this is one thing you could do, but I think the nice thing of visualizing the tree in this case is it starts to make it really obvious that you could do other things that could be better than just following whatever your current policy is, okay, or whatever policy you might have access to. And I'll just make this clear with the model and default. Okay. So we might instead, if we have limited amounts of computation, instead of just doing rollouts, we might want to try to get something that's closer to Q star. And one way we could try to do this is by trying to construct an Expectimax tree. So raise your hand if you've seen either Minimax trees or Expectimax trees before. Okay, like a few people, but not everybody. Okay, so this will be a quick introduction to those, but the idea is, if we think about what this forward search is, really what we are doing when we construct this tree, so this is the action, so this could be like say A2 and this is A1, and this is a next state. Imagine that you just have a few states in these examples. So the black nodes are all actions and the white nodes are all the states. You could think of this, and we've seen similar graphs to this a while ago, think of this as just sort of rolling out your Bellman backups. Okay, so you could think of what happens in the world is I take an action and I transition to some state, and then I take another action and I transition to some states, and sometimes I terminate. And what I would do normally in this case is then I would back up along this tree. So whenever I have states, I would take like an average or an expectation. And this is really just representing the probability of S prime given SA. So it's representing that sum. And then every time I have actions, I would take a max. And this is just representing inside of the Bellman backup that I take the max over the actions. So you could think of this as just approximating the max over ARSA plus gamma sum over S prime, probability of S prime given SA, V of S prime. Except for instead of having V of S prime, then you would just expand this out all the way until you hit the terminal state. Okay, and this would require us also to keep track of the rewards we obtain as we go down this tree. So, for example, here you might get reward of S prime A. So does that make sense? So if you have access to a Markov decision process and its dynamics model and its reward model, one way you could use that to figure out what's the optimal thing to do in your current state is you build this tree. Build this tree until at a leaf you reach a terminal node, or for a fixed horizon H. And then you back up by doing wherever you see it branching according to states, you take an average, weighted by the probability of each state. And whenever you get to a set of action nodes, you take the max. Any questions about that?
We might get to this later, but like if we're considering like complex games like Go,
Yes.
like the state space is like massive, right? It's very unlikely that you're going to run into the same like composition of the board twice. Like how do you deal with that?
Great question. Hold on to that. We'll get to it. Yes. Yeah, absolutely. So right now, well, and in fact, on the next slide, we'll talk about how big this tree is. Okay, but this at least conceptually should be something that you think, yeah, we could do this. I could imagine doing this. So why might this be better than before? Well, this might be better than before because you're not actually solving the whole MDP. You're only doing sort of Bellman backup starting from the current state you're in. And so you might imagine that if the space is enormous, even though you're sort of rolling this out in terms of this kind of exponentially growing tree, it still might be smaller than your whole state space. Okay. But as I was saying, this is huge in general. So if you want to actually expand the whole tree, in general, the size of the tree is going to scale by the size of your state space times the size of your action space to the H. H here would be your horizon. And so, as you could imagine, this is going to be terrible really quickly, right? Like we don't want to, if you think about Go or you think about Mountain Car or other games where you might be, or other environments where you might be having sort of 100 or to 1,000 steps, this is going to be completely intractable, right? But as you might notice, when we're looking at this, here when we wrote it out, we sort of thought about all the next states we could reach. But if that's a really large set, we know that we don't necessarily actually have to sample all of them and compute that exactly in order to get a good estimate of the expectation. We know that in fact we can just sample. So if you sample what's the next state 100 times and average over all of their values, that's a pretty good approximation of what the average value is, even if there are 10 billion states. Okay, because you can approximate an expectation by an average, and that tends to concentrate really quickly. So that's going to be one of the really big ideas of using Monte Carlo tree search, is that we're not going to have to expand all the next states, we're just going to sample them. Okay, so let's see how that might work. So this is where we get into Monte Carlo tree search. And note, I highlighted a tree here because we're not doing Monte Carlo search anymore. We're not just rolling out with a policy. We're essentially going to try to sample parts of that tree. Okay, but we're not going to just do single pi rollouts. So we're going to we're going to build a search tree rooted at the current state. We're going to sample actions in next states, and we're going to explore different parts of that tree. We're not going to always follow the same simulation policy pi. Okay, and then after the search is finished, we're going to take an action in the real world by whatever has the highest value as we estimate at the root. At least that's one way we could do things. We'll see some other ways to do it. And, well, let me just explain, give a little bit of intuition of why does this work. This works because what we're doing in this case So we are approximating expectations with averages. Okay, so we're not actually trying to expand all the next state, we're just going to approximate it with averages, and that will turn out to concentrate pretty quickly. And that's going to be really helpful. Okay, so let's do a quick check your understanding. So, oops, well, there you go. It's okay, you can think about whether or not you agree with this. Monte Carlo tree search involves deciding on an action to take by doing tree search. So think about whether it's a good choice for short horizon problems and why, long horizon, and large state and action space. And actually the middle of this is slightly debatable. So take a second and think about this. Cover this so that when I upload it later, people can. So why might the first part be false? Why would we not want to do this for, well, first of all, does anybody have any questions on what Monte Carlo tree search is doing in terms of how it's different than the other things that we could do? So then tell me why it's not probably a good choice for short horizon problems with small state and action spaces. What would you do instead in those cases? Yeah. We better do what?
Monte Carlo says.
Okay, so maybe, I guess what I was thinking more is in that case, maybe just do dynamic programming. Yeah, if the state space and the action space is really small, you can just do value iteration. Yeah, but in Monte Carlo research could work too. But in particular, if things are really small, if you think back, it's been a long time, I know, but in sort of standard dynamic programming, it's only like S squared times A for each backup, and then you're just doing that. If you're only just doing that H times, that's nice. You don't have any exponential dependence in that case. So if it's really small, just do Bellman backups. And the order of that is roughly S squared A times the horizon H, roughly. Okay, so at least it avoids the exponential. It will be a good choice for long horizon problems with a large state space and actions, small action space, because what we're doing in this case is we're approximating that expectation by samples. So we are approximating, so this is true, this is false, approximating expectation by samples. And so that means instead of us having to get that like enormous state space that we're multiplying by, whether S squared or such, we're just sampling from that. And so we can have something that's more like a constant with respect to how much we're sampling. Now the middle one is actually a little bit controversial, and we're going to see different ways to tackle this. Why should this be somewhat controversial? Well, in Monte Carlo tree search, the initial way we're getting a big gain is we're sampling next states instead of enumerating them. But it shouldn't be obvious that, like, for actions, we want to maximize. For actions, we want to take the best over all the actions. And so Monte Carlo tree search, a priori, still has to just sample the whole action space. And so it's not clear yet that unless we do something special, that Monte Carlo tree search is necessarily going to help us when we've got really big action spaces. Because in general, we've replaced the expectation by a set of samples, but it hasn't told us yet how to do anything smart in terms of the action space. Okay, so this one is sort of debatable. Maybe false. Depends how you think about it. But of course, there are a lot of algorithms that combine with Monte Carlo tree search to show us how we might be able to tackle this problem. Okay, so what we really want to be able to do is solve long horizon problems with enormous action spaces and enormous state spaces. And so we're going to need ideas beyond Monte Carlo tree search to tackle that. Okay. And upper confidence tree search is one idea for how to do this. And I think UCT came out in around maybe like 2007, 2008. People started using it for Go around then. And the idea in this case is that in addition to doing the sampling over next states, let's be strategic over what action we take when we're expanding in our tree. So when we decide to sample a next action, it doesn't have to be from a default policy pi. Let's think carefully about essentially where do we want to fill in our search tree. And this is one of those other really big ideas, because this is really where we're going to start to think about ideas from reinforcement learning, essentially to optimize computation. Because right now, we're still assuming that we know the MDP. Like we know what the dynamics model is, and we know what the reward model is. So in theory, if computation was no issue, we could just do value backups. The challenge is this is going to be completely enormous, and that's totally intractable. So the idea here is to say, well, maybe if we have access to those, we can still think of trying to approximate sort of like Bellman backups or approximate maxes, but we don't actually have to want to enumerate all the actions as much, and we want to really focus where we're using our computation. And DeepMind's been really a pioneer in thinking about using reinforcement learning to prioritize computation to solve a lot of really important problems, and I'll try to come back to that at the end. Okay, so how does UCT work? The idea is, and this is why I asked you guys about this and refresh your understanding, is we're going to treat each node that was sort of like a state node inside of our tree search as a bandit. And so it's like we have many, 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 many bandit problems inside of our search tree. And we're going to then maintain an upper confidence bound over the reward of each arm inside of a node. Okay, so the first node you would have is your root node. Okay. All right, and so it would have, say, A1, A2, A3. And we would think of that as a MAB, as a multi-arm bandit. Okay? And then when you get further down in the tree, so let's say this goes to next S prime, this would be another A1, A2, A3. And this would be another multi-arm bandit. Okay? And you'd have to store in memory lots and lots and lots of different multi-arm bandits. Okay? So you're maintaining huge numbers of multi-arm bandits. And just like what we normally do in upper confidence bound, we're going to maintain an upper confidence bound over each arm. But what we're going to be thinking of that is essentially what would happen if I take this action and then act optimally till the end. Now, one big challenge is, of course, we don't know what the reward would be of acting optimally. So there's going to be a lot of different sort of policies that are moving at once. But let's see what that might look like. Okay, so here's the idea. Okay, so let's say what we're going to say we have a node I. So this could be our root node, or it could be any other node. The way we're going to, I'm just going to call this AI, we're going to try to maintain an upper confidence bound over what is the potential expected discounted sum of rewards we'd get starting in this node and taking this action as the following. Let's say that we've been in that particular node and we have rolled out from it, using some strategy that we haven't really talked about yet, NIA times. So this is the number of times we've been to this node before and we've happened to expand the A action. What we do is we look at all the returns we've gotten under those cases. So what's a return again? So a return would be, go back to here. So let's say you've done this. What you would do, what your return in this case would be, is it would be a sum of all of these rewards you've gotten along the way. Okay, so G we're going to use to denote the return. So this would be this reward from starting in state S, taking A1, and getting the rewards out to the terminal state. And maybe next time you go down this action, you actually get to here and you get a different return. So those are just like your Monte Carlo returns from before. And it's just for all the other times you went through that action. Okay, so that's part of it. So that's just an average. And it's kind of a weird average, right? Because it might be that which nodes you visited and which actions you took have changed. So we're not committing it to be a particular policy. It's just like we've taken some action and we followed some, we've made a series of decisions till we got to a terminal state. We added up the rewards and we keep track of that here. So that's one thing, and that's sort of we'd probably look at it and think this is a very loose approximation of what the optimal Q value is for that state in action. The second term looks like upper confidence bound. which is you have some constant c, you have some log term, which depends on the number of times you visited this node, divided by NIA, number of times we've been in that node and taken that particular action. Okay, so this just looks like a bandit term. It's an upper confidence bound over the reward that we can get. And so what upper confidence tree does is that the way it picks the action, the next action to take from the current node, is it picks whichever one of these has this higher upper confidence bound. Now, it should seem slightly suspicious that this works because in bandits, when we took an action, we knew that this really was an unbiased estimate of the reward of that action, because we just would see that one action. And then we knew from Hofting that this really was an upper confidence bound on the true value of that arm. But now we're in a much more weird case, right, where we are thinking of this for a sequence of actions we're going to take. We're trying to do expectations over states, and the actual actions we're taking from this node onwards may not be optimal. You know, one time we might go through, I guess I'll draw it on the board. Like one time we might go through this zigzag, another time we might go through this zigzag, another time we might come back to here and then we take a different action. Okay, so it's not like we're not doing one step of policy improvement here. We just have lots of different things that we're trying and we're averaging over them. Okay, so you should be slightly suspicious whether or not this is going to be doing a reasonable thing. Okay, but it's certainly something you could do, something you could imagine coding. And then we'll do this many, many times, and then at the very end, so this will expand essentially different parts of your tree. Okay, and when you're following this, in particular, you're going to start to expand parts of the tree which look promising more. Okay, so if this one happens to have been getting, you know, this one gets like plus 100, and this gets plus 100, and this gets plus 90, whereas let's say one other time when you took this action, you went down here and you got minus 10, well then, when the next time you get to your root node, you're probably going to be more likely to keep going down this path. So it's going to sort of selectively expand parts of your tree. It's not going to hit, and you'll sort of have these like unbalanced trees where you'll often see like parts of things are getting filled in, and then maybe if something else becomes more promising, you'll switch to another part of the tree and fill in things there. Okay, so it's sort of this unbalanced construction of your forward search tree. And the way that it's unbalanced is that you're using the Monte Carlo aspect to approximate all the expectations, and you're using this upper confidence bound to sort of selectively prioritize across your actions. And that's what's going to help with our sort of enormous action space. Now, you still might be concerned that when there's really like a really enormous number of actions, like we're going to see in Go and other cases, that this still isn't going to be enough. Right? Because if the number of actions you have is like, you know, like 1 million, these things generally, you'll have 0 for this part, right, before you have taken any actions, and your counts will all be the same. So it should still be concerning because, like, what should you do if you have these 1,000 different actions and, like, you might not be able to do anything essentially until you visited everything once. Because before then, as long as you've defined something that's a reasonable upper confidence bound, everything is going to look awesome. It's like, oh, action 99 will be awesome. Action 100 will be awesome. And so you'll have to sample all of them at least once, and that generally will be completely intractable. So we'll see ways to further reduce this, but what you can think of this part as doing is saying, well, if you can at least sample every action once, you can at least mean that you're not going to have to focus on unpromising actions later because you're going to quickly use this upper confidence bound. So these sort of Monte Carlo tree searches were starting to look really promising. You know, a lot of people have used tree search-based algorithms, as some of you might have seen other machine learning algorithms, or sorry, other AI classes probably in particular. But what this Monte Carlo and UCT-based approach is there's sort of this highly selective best first search, but with simulations as well. And they're using sampling to break the curse of dimensionality, and UCT to help with large action spaces. Okay. And the other really nice benefit of these ones is they're parallelizable. So when you're sampling things, you could certainly imagine trying to expand, do these sort of rollouts many, many times, and then sort of collect the results. So you can start to parallelize these methods as well, and that's going to be really helpful. Okay, so that's the background between Monte Carlo tree search. But now, of course, the really big breakthrough that this allowed, or people built on these ideas, is to achieve AlphaGo. AlphaGo, and then AlphaZero, and then Mu0. So there's a whole sequence of them. And let's just get up a movie for that for a second. And who here's played Go? Okay, a few people. I was thinking it could be fun to have us all play it so we can see that it's really quite hard. Good. But another time.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
Building suspense. We'll see how the network goes. This is a documentary of DeepMind's efforts to try to beat the world-class people in Go. Let me see if I can make it work. I think it's probably decided it doesn't like the internet right now. Let me just double check that if I can get that to work. So what they ended up doing is they're going to use reinforcement learning to help solve this problem. We'll see whether or not the technical difficulties resolve. And then what they did is they started playing against grandmasters, and they played against Lee Sedol, who was one of the best people in the world at Go. And I think one of the really interesting things about this is that it really shows that it's now possible to use AI to beat the best people in the world at Go. But also the types of strategies that it built were very different than what people were doing before. And so I think this is a pretty important aspect for AI, because we've also often thought of AI as sort of automating things that people already know how to do. And I think this illustrated that there are really starting to be places where computers go beyond even the best humans and what we know how to do. And since then, there's been a recent paper, I think maybe a year or two ago, by Bean Kim, trying to look whether or not you can teach grandmasters using the strategies that AlphaGo and its descendants invented. And so then there's this really interesting opportunity and question to think about, can we actually learn from computers in these new ways and try to sort of exceed both human level performance and computer level performance. So I will post this later. You guys can look at it. Let's go back to there. Okay. All right. So how does Go work? Well, it's a really, really old game. It's considered sort of one of the classic hardest board games, and it was considered a grand challenge for AI for many, many decades. The sort of game tree search that we saw before, something like a forward search. Now, it couldn't be Expectimax in this case because it's a two-player game. Go is what's considered a zero-sum game, meaning that someone either wins and loses. And in this case, whenever we sort of think of a next state, rather than it being an expectation, it's really a mini-max problem because each opponent is playing to win. So in this case, it's good to think about sort of, what is actually uncertain in this case. When we're playing Go, the rules of the game are known. They actually have another descendant now where you didn't have to know the rules of the game, but certainly for the first few, the rules of the game were known. So what's unknown in Go if we wanted to think about sort of building a tree or trying to learn in this case? Like, if we know the rules, yeah.
Well, you might expect your adversary to play the best move. That might not always be true. They might be seeking different strategies, so you wouldn't know that.
It's a good point. So it might be, as I was saying, that you might not know exactly what the best strategy is, or might not know whether someone's going to play the best strategy. I think the other thing that I think of is that we don't always know what the best strategy is. It's just incredibly hard to compute this in this case. And so in this case, that sort of next state, if that next state is really from an adversary, it's not clear. You've got stochasticity in that because you don't know what the optimal game is. Now, of course, once someone picks a move, everything is deterministic. So in some ways, it's all deterministic, it's all known. The key thing is that because it's sort of this adversarial game, it's not clear what the optimal strategy is. So that's kind of one of the really hard parts. All right, just a couple basics of the rules of Go. So normally it's played on a 19 by 19 board, but when people first started to, kids and also when AI researchers started tackling this game in earnest, starting like the late 2000s or 2000, David Sildor, who's one of the authors of this and an amazing researcher, I think as part of his PhD in the late, like 2008, 2009, he was doing things on sort of a 9 by 9 board. And just as a couple basics, there's two different players, either someone playing the black stones or the white stones, and you're trying to surround stones that are captured. And then you win there's, as I said, it's a 0-1 game. 0-1 game, which means a winner takes all. One of the interesting things about Go is that in general, there's no intermediate reward. So you have to play till the end of the game to see who's actually winning. And so there's just a single reward at the end, which also makes it very hard for credit assignment and to understand what moves caused, the resulting game. So AlphaGo and AlphaZero. AlphaGo was the first one that was used. Then they developed a number of variants. They then played against Lee Sedol. And then there was AlphaZero. And what they exhibit in this case is a number of different really interesting features. So they have self-play, strategic computation, highly selective best first search. They use the power of averaging. They leverage local computation. And then they learn and update heuristics. For those of you that have seen tree search-based methods before, you've often probably seen ideas around heuristics, which are other ways to sort of think about how do you expand the tree. One of the interesting ideas in these papers is that they're going to learn those heuristics and update them over time. That's another important aspect. So let's see how it works. So how does self-play work? So the key idea in this case is that we're going to have the agent play itself. So you can think of it as there being two copies of the same agent right now. And what will happen when they're playing a game is they compute the best move at the current state, and then the opponent does the same, and they have access essentially to the same policy or the same sort of algorithm, but they're both just using it in an adversarial way. And so that means like the only bottleneck in this case is computation. We have no humans involved. And self-play also provides a well-matched player. So take a second and think about like what are the benefits that will happen with self-play and what's going to be like the reward density. Are there going to be lots of rewards when you do self-play? Are there going to be very little rewards? And let's just take a second and I'll check and see whether I can make the networks work. Maybe talk to our neighbor and see if you guys both have the same idea of whether self-play will be helpful or not. All right, what does this do to policy training? What happens when you do self-play? Like, do you have high reward density? Do you have low reward density? What happens? Okay, raise your hand if you think you have high reward density. Raise your hand if you think you have low reward density. Okay, so there's. All right, was somebody who think we have high reward density want to explain why? That's right, we do have pretty high reward density. Why do we get that when we do self-play? What happens? Or I think it's maybe easiest to think of like, if you play against someone that's much, much better than you, what happens?
Just kind of
Lose all the time, right? Everyone's probably done this before. You play against like a friend of yours is maybe much better at a board game than you or something like that, right? Or your friend of yours is much better than you at tennis or something. And you go and play with them and it's not normally that fun because you just lose all the time. And when you lose all the time, you may not get very much signal about what things are even doing better or worse at because you always lose. Okay, and so that would be a case where the reward density is very low because the players are really mismatched. And it means that most of the time the agent is not winning. Now, the same thing is true if the agent is much better than the other agent. But self-play means you're sort of matched, you're like matched at the same level as someone who plays tennis the same level as you, or you're matched with someone who has the same ELO score as you in chess or Go, which is sort of a way to quantify the player's skill. And the nice thing about that is that you would expect that roughly, if you play someone that's exactly the same level, now here you're an RL agent, so you're going to play someone that's actually you, just on the other side. So they're exactly the same level as you. And that means you'd expect you'd win about half the time, like on average. So that's really good density for something that is a 0-1 game, because you're not just like every 3,000 games getting a 0 or a 1. Here, about half the time you'd expect to get a 1 and half the time you'd expect to get a 0. And the reason that might be beneficial is hopefully that's going to give you a lot more signal of how you should change your policy in order to figure out how to get better. So I think that self-play is a really interesting one because you could think of it in some ways as kind of providing an automatic curriculum. I'm going to have it on the next one. So the rewards are going to be pretty dense. And for those of you that have seen curriculum learning before in other machine learning stuff, just like in classes where you often sort of build up with math over time and you don't start with calculus, you start with like addition or what a number is, and then you slowly build up so you're always trying to be on roughly the right level. Similarly here, the agent should do that automatically because they're going to start off and they're going to both be terrible at Go, but they're still going to get pretty high density of reward because they're both terrible at Go. And then over time, the agents are going to get better. And then now they're automatically always playing an agent that's roughly the same level as them. Now, we'll have to see why the algorithm will help them get better, but intuitively, as we saw even with like the Monte Carlo simulation, not even tree search, there it was doing like one step of policy improvement. So you can imagine that even if each round we're just doing kind of like one step of policy improvement, over time we would hope that we're going to get better and better. Okay, so this idea of self-play I think is a really interesting one. It works really well in games, and it's been exploited a lot. I've often thought like it would be really interesting to see are there other places you can set up to essentially be like a game. Because what you could think of here is what self-play is leveraging is that sort of for the dynamics part of your environment, you now have a simulator you can plug in, which is the agent itself. Now, in general cases, you can't do that. Like if I'm going to simulate patient dynamics, I can't just plug in like, I can't do self-play for that, right? Like an action is how the patient responds to some treatment. And I can't like play against two patients. That doesn't make sense. But I think in some cases here, it's really a very reasonable thing to do to use self-play, and it can be really efficient. Because you can think of it in a way as like it's changing the strategies in a way that's sort of iteratively updating the complexity of the environment you're trying to solve. Okay, so one.
I think I have a good idea, but what is the exact definition of reward density? What is events with respect to?
Good question. So here I just mean about, could mean lots of things. Here what I mean by reward density is how often you're going to get you're going to win. Okay. So here rewards only happen at the end. So it would just be of the games you play, are you going to get a lot of reward? You're going to get 0. And if the agents are really mismatched, in general, the reward density is going to be either saturated, which means you always win, or near 0, because you're never going to win. And neither of those are very informative. And the idea is that if you're getting reward about half the time, that might be really informative, because you can you get lots of signal of like, that thing worked, that didn't work, that thing worked, that didn't work, And so you're going to have a lot of stuff to estimate kind of a gradient or an improvement for your decision policy. Yeah.
With self-play, can we say that like if you play against someone who has like a completely new strategy, might not be able to generalize well enough because I was always playing against myself and who is using the same kind of strategies?
Great question. So yeah, that's a really great question, which is, okay, well, so self-play might be good, but then what if you suddenly play against someone really different? So what we're going to have to see in this case is whether or not over time you do get to something that's essentially like a mini-max policy. So if you get to the optimal policy, you could hope that you really are at, like Grandmaster or beyond. And one of the exciting things here is that they will get to that. So as this ratchets up after lots and lots of training, and after using very, very complicated networks, you can get to that level.
Does that work? Well, does that work for like games where moves are not like deterministic? like I don't know, like gambling games like poker or something, where there is some sort of like probability associated?
Yeah, interesting question. So there's also been a lot of work. There are really, really good AI agents for poker now. I think it was 2019 that Noam Brown did a paper in Science showing that you could beat, I don't know if you could beat, but it was certainly sort of competitive with top humans, I believe. So Thomas Sandholm and Noam Brown, who did his PhD at CMU, have got an agent to do well at poker. The algorithms are slightly different, but yes, you can this. But it's a good question. Here, we're assuming that it's also going to leverage the deterministic nature. Yeah. All right. Okay. So how does this work? Let's go through sort of what it's doing, because it relates to upper confidence tree search, but there are many changes. So there are many improvements that were needed for it to get much better. But it is going to be similar in the sense that it's going to try to compute. First, we're going to start with, it's going to simulate many, many, many games, and it's going to iteratively try to learn better strategies. One of the things that is going to be different compared to sort of naive upper confidence tree is that we're going to actually maintain a neural network. So let me just get back to there. Okay. So what we're going to do in this case is we're going to have a neural network that, given a state, can produce both an estimate of V of S and a policy distribution for that state over actions. So we're going to maintain a single neural network. This is what AlphaZero does. It maintains a single neural network that, given an input state, will output both an estimate of the value of that state and a policy for that state, a distribution over actions. Okay. And we're going to talk about how we train that shortly. But for now, just assume to start that we've already trained that, or that we have access to that. And we're going to use that now when we're going to do we're going to play a number of games. Okay, and in particular, let's first think about how we're going to compute the first move in a single game. So we're going to do self-play in this case between two agents, but I'll use the same. What we're going to do is we're going to do an upper confidence bound based thing. Okay, what is these upper confidence bounds going to be based on? And then we're going to decide the max between them. So this is going to look like UCT, but slightly different. So what U is going to be equal to in this case, so U of IA, so let's say this is node I, it's going to be proportional to the following. It's going to be proportional to PSA, which it is A divided by 1 plus NSA. Okay, this is from our policy network. I'll write it as this. So this is from our policy network. This means that our upper confidence bound is going to include in it a bias towards some actions versus others. So our policy network is going to say, if you give me a state, I will give you a distribution over actions. Okay, and that's this. And that is going to help us with the fact that we have an enormous number of actions. And so this is going to prioritize some actions that we think in general might be better for these types of states. So this will be a deep neural, like that neural network up there is going to be a huge, crazy deep neural network. And is going to try to leverage similar types of states to suggest which actions might be useful in this particular state. The other thing you can see here is that this is going to decay as we visit a state in action more. Here in this case, so I'll just be a little careful. This is all going to be operating, I believe this part is really I, so this is, I think, at the node level. I'll double check that, but the PSA has to be at the state level. So remember, you'll be in some state at this point, and you could feed this into like a convolutional neural network. It's an image of the board, or some other deep neural network. So that part has to generalize. But I'm pretty sure, I'll double check this, that the count here is actually specific to this particular node. Now, why is this U interesting? It's interesting both because it incorporates sort of a priority function over actions. You might say some actions are better or worse, and that's going to change which ones we expand. The other is that we are decaying faster than normal upper confidence bounds. So recall that, like UCT, U is proportional to 1 over square root. Okay. So this is going to decay a lot faster. This means we're being a lot more aggressive in our upper confidence bound. We're shrinking fast. And so what that means is that we're going to do a lot less exploration of things that we think are not so good. Okay, so that's one really important part of how we're going to pick what to expand. The other part is this notion of Q. So how are we defining Q for this node? Q is going to be equal to 1 over n by a, and again, I'll double check this is nodes rather than states. Sum over s prime, b of s prime. Okay. What this means here is that this is going to be an empirical estimate of what the value is over the states that we've reached by following this particular action in this node. Okay, and we're going to see where that comes from shortly. Okay, it's going to be a little bit different than what we saw before. But these are the two components that we're going to use to decide which action to expand. So, yeah.
By referring to the node here, we're talking about the identity of the node in the matrix or the state of the node and the state?
The state. The state. So you can think of sort of like what a node here is this case is it is a particular board game configuration. So it's like saying the white pieces are here and the black pieces are here. So it's like you could think of it as just like an image of the board. Okay. And the earlier work, in fact, was using convolutional neural networks to take in essentially images and features. Yeah?
Is there a meaningful difference between nodes and states?
Yes, so it's a great question. So in general, there may be a difference between nodes and states because, well, this is, I'm not a Go expert, so I don't know. But in general, for these type of algorithms, you could reach the same state as at different parts of the tree. And if you can do that, then you would have different bonuses there. Now, I don't know enough about Go to know whether that's always possible. And it's certainly possible in some cases that, you know, it would be isomorphic, that like the nodes and states would be identical. But in general, these sorts of algorithms can work in cases where you can certainly imagine for like checkers or chess and stuff, you could end up in the same board game state later on, but it would be a different part of the tree. Okay. All right, so this is just the start. This is just starting at the root, trying to figure out which action we're going to take from the root. And then what we do is we repeatedly expand. So in this case, we would follow the right-hand side. Now, what we would do at this case, which is pretty interesting, is so this would deterministically, you know, I would put down, say, a piece on the board. In this case, I decided to put down this piece. Okay. And then what I would do is I would flip over and pretend to be the opponent, and it would do the same thing using its Q and U. Okay. Now, its Q and U are going to use the same neural network approximation. So this is just self-play. But it's just useful to know in this case that they're going to be optimizing for the opposite. You know, one's trying to optimize that the black pieces are going to dominate, the other one is going to try to optimize that the white pieces dominate. So now we're going to have that the opponent selects the max Q plus U. So it's just useful to think of like, you know, you're sort of repeatedly flipping back and forth between these two, but you're using exactly the same neural network parameters when you do that. Okay. So this is going to continue going all the way down until we hit a leaf node. So we just read, this is again, we haven't even selected a single action to take. All of this is going to help us finally take a real action in one game. So right now we're just going to do a whole bunch of computation to figure out what that action is. Okay. And just to note again here, so we're assuming that we have access to this parameterized deep neural network. And whenever we do this expansion, we are using our P function because that's what was going into our upper confidence bound. So our U was a function of P. Okay, so it's a function of these probabilities. And so we could weight different actions more. So we keep going all the way down until we hit a leaf node. And at that point, we plug in V of S. So when we hit a leaf node, so if this is terminal, we're going to do V of S. We're going to use our neural network to plug in V of S. So this is different than what we saw before, because before we were thinking we'd actually get the rewards along our trajectory until we get to the final end. Or if we didn't have any rewards, we just get whether we sort of thought we were in a winning or losing state at that point. We're not doing that anymore. We're plugging in an estimate of the value of the final state according to our value network. And that means also that we can either go all the way out till we win or lose a game, or we can terminate. We can, say after 700 steps, plug in our V of S, which would give us an estimate of how likely we were to win the game at that point. So once you have that, we're going to propagate all of this stuff back up. Okay. So if we're going to select that, once we go all the way down and we get to some V, this is going to go back up. And remember, what this is going to do is we're going to update our Q function. So our Q was equal to 1 over NIA, sum over all of our times V of S prime. So we're going to update our value all the way back up. So we used our P function when we were expanding out to figure out which actions to take, as well as our upper confidence bound. And then we use our V prediction to do the backups. So the way that it would work is we go all the way out to a leaf node, and then we go all the way back up along the ancestors to the root node, and then we do the whole thing again. We do that many, 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 many times. I'd have to remind myself, I think it's like, say, for example, it might be 160,000 times, for example, just to give you a sense of the scale. So it could be something like 160,000 times, and that means you're going to fill in parts of the tree. And then after all of that, we have to decide what actually to do. Okay, so that's just to compute a tree to decide the current move. Okay, so we do this many, many, many times. Okay. So we do this many times, and then at the end, we are going to decide what to do at our root node by the following, and this again is a little bit different than what we've seen before. We are going to compute a policy for the root node by figuring out which actions did we mostly visit underneath it. So we're going to look at NSA, so sort of which actions, how many times did we take each of the actions from the root node to 1 over tau. Which I think this should be minus, let me just double check. Yeah, well, I guess it just depends how you set tau. So tau is just going to be a temperature parameter. Okay, so if tau, for example, was -1 in this case, then it would be 1 over NSA. It would be proportional to that. Or if n was 1, you would be sort of proportional. You would take things according to that divided by the total. So if n is 1, if tau is 1, tau is equal to 1, then it would be NSA divided by n of s. And as you increase or decrease this, then you get things closer to taking a max or just averaging. So this allows you to sort of like have a stochastic policy at the root node instead of necessarily just taking the argmax. So this is quite interesting. So this is what they're going to end up doing. After you do all of this, you're going to actually take an action, and then you're going to sit. So that gives you a policy, and then you are going to sample from that policy to actually make a decision. Okay, so this is how a game works. You do an enormous amount of computation. At the end, you get this policy according to the number of times you've taken each action from the root node. And then you sample from that policy. You reach a new state. So like, let's say you put down that board, thing. Then the opponent does exactly the same thing. And they put down something. And you repeat this all the way out until the game ends. Now, even if you're DeepMind, you care about computation, and so in some cases they will truncate games if they think there's definitely going to be one outcome or the other. Okay, but in general, you would just keep going this all the way out, and Z here would be who won or lost the game. Yeah.
So you said they will truncate games, but like, how do they actually sit behind the computer and watch the games being played, or like?
No, it's absolutely all automated. So this is going on, billions of times. And what they will do is if like, I think it's after 700 moves, if they're not sure, if they think either it's going to end in a draw or it's definitely going to be a lose. And then they try to bound like false positives and stuff like that. But it was interesting to me that they included that. Just indicates that it probably saved them a substantial amount of computation time. But yeah, no, everything is totally automated. Okay, so what they do is now, at this point, so this is like a single game. As you could imagine, this is an enormous amount of computation. After a single game, but a lot of this could be parallelized. we are now going to train our neural networks. So remember that we used a neural network to both give us an estimate of the probabilities, like give us a policy for each state, as well as a value. And what we do is now we have, so from that game, that one game, we have one observation. So this is our Z. Know who won? Who won the game? And we had, from each step, we had these policies that we computed. And we're going to use those as targets to train a neural network. So what we do is we go back and we say, okay, well, in that time when you were in state S, and you computed a policy, and eventually you got a value of Z, you either won or lost the game, we are now going to train our crazy big deep neural network to predict for this state, this is the policy, and for this state, that is the value. And this is just a supervised learning problem. And then they do the same thing for every state that was reached in that particular game, all using the same final state, which is either you won or lost. Okay. And so this is just an enormous network. I can't remember, I think it's maybe like, let's say, 40 layers, and they try, and we'll see shortly, like the influence of architecture too. The architecture matters. But, and so again, just this neural network goes directly from states to both predict, it's got two output heads, both predict policies and values. In their earlier work, they had separate neural networks, but one for policy and one for values. Here they just combined it. All right, so that is sort of like how it works in a nutshell in terms of what they're doing. And then they do this for an absolutely enormous amount of time. The final thing I think was trained for 40 days over like many TPUs, et cetera, yeah.
Mean like if you think about this is kind of like a loss function with respect to the value, the policy is not actually a component of that loss function? Is that what?
Yeah, that's a great point. So what you said is a really good point. So these are just two different heads. And you can think of it as what they're sort of assuming in this case is that the representation you're learning is going to be helpful for both. But this value may or may not relate to this policy. And this is just saying, like, we think that like the features we're going to learn about this, like the sort of way that we're encoding the game states. And also just to note here, it's not just the current board that they're using. The states they use tend to use history as well. Because, again, I'm not an expert in Go, but there are various rules in Go which mean, like, I think you can't repeat a move and stuff. So because of that, they have to maintain a short history of the previous game states. So you can think of S really as being like multiple game board states of the past. And I think the intuition for this is that you're going to learn feature representations from that that are going to be helpful for predicting both of these. Now, ultimately, you would hope that this sort of, there is some relationship between these two, but they're not constraining it. So just to recap, what are the key features that they're using? So I guess also to specify in this case, they're going to do this across many TPUs over many, many, many days. And what they're doing when they do this is that they're constantly retraining these neural networks. And at the end of all of this, when they actually play kind of test games, say against other human players or against other AI agents, is they're going to still do the Monte Carlo tree search. So they're going to take sort of their final neural networks, and then they're still going to do the Monte Carlo tree search method that we've just seen before they make decisions. And so we'll see in a second sort of whether that's important or not. So in particular, some of the important questions that they consider in this paper is, what is the influence of architecture? Does it matter which architecture you use in these cases? What is the impact of using MCTS? Obviously, they're still learning a policy and they're learning a value function. And the question is, how much additional gain do you get, even after 40 days of training this by doing Monte Carlo tree search? And how does it compare to human play or using human players? So the first way that they did this is instead of having this neural network that was predicting a policy and a value, is they'd actually did supervised learning on human play. And that gave you a way to prioritize actions. So that's what they'd done when they did AlphaGo to start. And I think that's what they did also for when they won against Lee Sedol. And then what they've been trying to do in this paper and others is to kind of remove some of those assumptions to see if you could learn without even human knowledge. Now here, I'll just specify that they still know the game rules. And then they have later paper where they want to not even need that. But here the algorithm is. So the first thing to note is that higher is better. This is talking about the performance of the resulting approach under different architectures. Okay, so what they do is they actually have the same training data that they use, and then they just use different architectures. They use data in this case from some of the runs of AlphaZero, which is the algorithm we've been talking about. So all of these have the same data, and then they look at what the performance is if you train the neural networks with that data. So same data, just differences architecture, and there is a huge difference. Okay, this is like from 3,000 to 4,500. So their current one, so this is a convolutional neural network, which is separate, meaning that you have a different policy network from a value network, whereas this is a ResNet, and they're using a dual representation. So you can see that you get a significant benefit by leveraging representational strength across both of these targets, and also that this is better than using convolutional neural networks. So I think this is a good reminder that like when we're doing reinforcement learning or we're doing decision making, we still want to build on all the amazing advances that are happening in deep learning in general, and the complexity of the neural networks that we use and the functions they can represent really matters. Okay, so that's sort of the take home from this part. This is a huge difference in performance. The second is the impact of Monte Carlo tree search. So I think this is important to know. This is if you use the raw network. So you take the network, I think this is after those 40 days of these crazy numbers of TPUs, and you don't do Monte Carlo tree search on top in kind of your evaluation games. And again, this is much, much, much worse. Okay, so this is AlphaGo 0, the algorithm we've been talking about. AlphaGo Master was another one they developed shortly before this. This is the one that beat Lee Sedol. AlphaGo, what they call FAN, is sort of the first big AlphaGo paper. And these are some of the other approaches that happened before their methods. And again, you can see that even though they now have all this beautiful different architecture, et cetera, if you don't do Monte Carlo tree search on top of that, you miss a lot. So it really is important to do this last mile of additional computation, even after you have these really, really good neural networks. This kind of local computation matters. This gives you a sense of sort of the training times involved. So this is the Lee Sedol paper, or Lee Sedol method. I don't think they published this before. This is sort of one of their master methods they had. And this is showing for a particular size approach how long it took of training before you got something that exceeded all of those. So it gets there, but it also just highlights sort of the enormous amount of computation needed and the importance of the architecture. So I know we're almost out of time, but I just want to highlight two things. So again, in this case, it didn't need any human data, no supervised learning. And they noted, though, that it was less good at predicting human play than some of the other prior methods. So that, again, just highlights that these methods really are helping agents to discover strategies that are not necessarily the ones that are used by humans. They're discovering different ways of solving these sort of incredibly complex optimization tasks. And I think that's really interesting in terms of sort of the future of human-AI collaboration. We're almost out of time for today. I'll just highlight as well that these sorts of ideas of how to use RL to optimize computation and solve really, really big search problems have also been used by DeepMind to solve things like alpha tensor and these other ways of sort of trying to start automatically searching for new algorithms, which I think is really, really exciting because you can think of sort of the space of algorithms or the space of sort of different search algorithms, et cetera. And those are enormous, and so you could think of using these types of strategies to prioritize which things are most effective. All right, so I'll leave this here because we're out of time. You're welcome to look at this to think a little bit more about the aspects of UCT search. And then on Wednesday, we're going to think more about rewards in RL and what are the implications of which ones we're choosing. I'll see you then.